Okay, so yeah, today we're going to start chapter 21, I'm sorry. I did the chapter numbering this way, just not to confuse with the physics 1 stuff. But chapter 21, second week of physics 2, the general idea is we're going to look at, last chapter we did Coulomb's law and electric fields. And now we're going to talk about some things you can do with electric fields, talking about electrical energy and eventually the idea of capacitance. So last semester in physics 1, we had gravitational potential energy. That that gravitational potential energy was if you brought something up a height y, it would gain potential energy equal to mgy. Potential energy was not energy really accomplishing anything, but it was the potential to turn into something else. In the case of physics 1, it was the potential to turn into kinetic. That when you lift something up, you're giving it energy that can turn into movement. It was based around gravity. Gravity was a force down of mg, and the potential energy was due to the moving in that force. And it was basically what it was based off was the idea that it was when we moved the object through the gravitational field, we could increase the potential energy. How far we moved the object in the gravitational field was how much we added to the potential energy. And I'm using this terminology on purpose, that it was in the moving it in the gravitational field. We also, if you remember from that stuff, we talked about how work was change in kinetic energy, or negative change in potential energy, and work was Fx cosine theta. There's some equations from work that I'm going to come back to as we do this. Now, the reason I'm bringing this up is now we have, instead of gravitational fields, we have electric fields. And so we can talk about what happens when we start moving things in electric fields, comparing it to what happened when we moved in the gravitational field. See, potential energy is always related to a force, no matter what type. In potential due to gravity was related to the force of gravity. Potential due to a spring was related to the force on a spring. Well, in a potential due to electrical will just be based off the force of the electrical force, or the Coulomb's force. But either way, when you're in the presence of a force, potential energy will decrease when you're moved with the force. That this ball, gravity pulls the ball down, and therefore its potential energy decreases as it moves down. And so as this guy goes down, he goes with the force, he decreases potential energy. When you go A from B, the potential energy decreases. Now let's say instead of a gravitational field, we have an electric field. And I'm going to set up my electric field basically the same way. So it's just going straight down, because the electric field goes from positive to negative. And so I have two plates of charge, a positive charge at the top and a negative charge at the bottom. This means that there's an electric field pushing downwards. And if I put a positively charged particle in that field, there's going to be a force acting on that positively charged particle pointing downwards. And if you let go of this charged particle, it would move from A to B. And what you can see is this looks kind of the same. That one is just gravity pushing it down, and the other is just the electric fields pushing it down. But otherwise, it's the same basic setup. Now, I can still say here that when we move from A to B, we would be decreasing in potential energy because we're moving with the force. One thing that is different between this and gravitation, though, with electrical and gravitation, is if I was to put an electron instead, a negatively charged particle in instead, the force on a negatively charged particle, because remember the fact, oh, here's my mouse, that the force on a charged particle in a magnetic field is QE. So if Q is negative, the force is in the opposite direction of the electric field. And so if I put a negatively charged particle in here, the force is actually going to be upwards. And so if it's a negatively charged particle, if I move from A to B, I'm actually going to find that my potential energy increased because I'm moving across from the force. But let's look at all three of these cases. See, for all three of these cases, and I need to move the picture of me to take up less room on the screen. For all three of these cases, when I move from A to B, I can say that I'm going to have a change in potential energy, where the change in potential energy is just going to be the final minus the initial. So when this guy goes down in here, his change in potential energy would just be the potential energy at B minus the potential energy at A. Though in this case, the potential energy at B is 0. That means my work, which is always force times displacement, cosine theta, but I'm ignoring the cosine theta because I'm doing everything in straight lines right now, is just negative potential energy. Or the change in potential energy is negative F delta X. Now the gravitational force, since it's mg, means the change in potential energy is negative mgx, which is something we had covered in physics 1. But I can use this logic. See, if I use this exact logic, I can say that when this guy moves downwards, the change in potential energy can be given as the potential energy of B minus A. And work is force times displacement, or negative PE. Well, I can also say that the change in potential energy is negative Fx. But here F was QE. And so I can say the change in potential energy is QE, the displacement, with a negative sign. For the last guy, if I use the same logic, it'll start the same. This will look the same. This will look the same. Except here, if you notice, I added another negative sign. I said negative F delta X. I did that because I'm moving against the force. And so it's actually going to be a negative value from the force. Really, the force isn't what's negative. It's the delta X it's the delta X that is negative, that I'm going in the opposite direction as the force. It comes from the Fx cosine theta, that F is one way, X is the other. They're 180 degrees apart. And so I still can get the same logic. Now, I do get off by a negative sign, so it seems like I'm getting a different equation. But keep in mind, Q is negative. And since Q is negative, you get two negatives, you get a positive, it's the same thing. And so I can use this and say, just by comparison, for physics 1, we had all this stuff with potential energy. Potential energy was mg delta y. I put an X there just because I was matching the equations. But it was mg delta y. Logic, and you can see the same logic, I can get to the same spot with these electric fields. So it comes to show that the potential energy from an electric field, if you have a uniform electric field, or the potential energy between two plates, must be going as QE delta X. Now this makes some assumptions. The first assumption, the big one, is a uniform electric field. And it's kind of a nice thing that if you have two solid pieces and a positive charge and a negative piece, it'll actually have a pretty good uniform electric field between them. I showed last class a video of an electric field between two plates, and you saw the not last class, Wednesday's class, and you saw like the metal shavings kind of move in a straight line. But if you get a uniform electric field, there will be a potential energy change between the two plates. Now, I'm not defining necessarily potential energy as 0 at either spot. You notice this marks as high potential energy, low potential energy. But I'm just saying if you move within that region, you have a change in potential energy. If you go from A to B, you will have that change in potential energy, as long as it's a uniform field. Going further with stuff that I have already said, but I'm just stressing. A positive charge loses electric potential energy when it's moved in the direction of the field. So if it goes with the field, its potential energy goes down. A negative charge loses electric potential energy, moves in the direction opposite the electric field. So a negative charge will move in the opposite direction. Once again, if you just keep the equation the same, and if just Q is negative, plug in a Q negative value, it will work. But we know energy can't come and go from nowhere. Conservation of energy. If something is losing potential energy, it must be doing something else. And the idea is when these charged particles are moving in these electric fields, if they are decreasing potential energy, that means they're increasing kinetic energy. And what happens if you put a charged particle in an electric field? It feels a force. We covered that last chapter. That force, F equals ma, that gives an acceleration. And so what's going to happen is if you put a charged particle in an electric field is it'll lose potential energy and start moving. And that potential energy will become kinetic energy. And as it gains kinetic energy, it will, be moving. Does that make sense so far?
Mm-hmm.
Now, here's the thing. This potential energy depends on the charge of the thing, right? It's QE delta X. And so let me go back to my picture for a second. If I change the charge of my particle within this electric field, that's going to change the potential energy. The same way that if I go from lifting this guy up and down to lifting like my entire water ball up and down, they have different potential energies because I'm changing the mass. What is found to be simpler for dealing with electricity is to talk about how much the potential changes between 2 points for a unknown amount of charge. Basically, we're going to divide out the Q. And instead of having negative QE delta X, we're just going to talk about negative E delta X. And when we do that negative E delta X, we can say that between 2 spots, for any charge, we can have a certain amount of potential difference. Potential difference is not the same as potential energy. Potential energy is Q, it's negative QE delta X. But potential difference is just if we get rid of that, divide out that Q, the potential energy divided by Q, how much it changes between 2 points. And this is just the final value minus the initial value of the potential energy over the charge. Now, I keep calling it potential difference. Actually, that's not really the real name. The real name is electrical potential difference. The thing is, electric potential difference is a mouthful. Now, units is a joule per coulomb because it's energy over coulombs. But joules per coulomb is used so often that it got the name V, or volts. Sorry, it got its own thing, volts, symbolized by V. And what happened is when people kept talking about electric potential difference, people got really sick of saying electric potential difference repeatedly. So they said, screw that. Let's call it volts. Or voltage, I mean. So when you hear the term voltage, voltage is actually a shorthand nickname, basically. What voltage is electric potential difference. It's just, it sucks to say electrical potential difference. And since electrical potential difference has the units of volts, we just call it voltage. So whenever you hear voltage, that's really what you're talking about, electric potential difference. Now, voltage is a scalar. All of those vectors we dealt with last chapter, don't have to deal with them here. It doesn't matter what direction it's in. Same way that energy is always a scalar. But this is a weird scalar. It can be negative. Because voltage, also known as, once again, as electric potential difference, is a change in things. It's not just V, but V, there's 2 V's subtracted from each other. It is possible to be negative, which is weird for a scalar. But yes, it can do it. Now, voltage you've probably heard of before. Voltage you may think of as, what drives electrical devices. You have like 120 volt wall coming out of the wall. That's what makes your computer go. Why that is, we will get to in a little bit. So if I go back to this picture I had before, and I have a charged particle going from point A to point B, feeling that force of QE in this uniform electric field, I can say that its potential difference, it's not just, you don't just have the potential difference of a spot, you have the potential difference between 2 spots. And so the potential difference, or delta V, would just be the potential at B minus the potential at A. Well, that's going to be the change in potential energy over Q. Now keep in mind that the change in potential energy is negative QE delta X. And so therefore, potential difference is negative QE delta X over Q, or just negative E delta X. And that is the equation for potential difference. When you have a charge moving in a uniform electric field, the potential difference is negative E delta X. If the electric field is not uniform, you need some calculus. It's actually going to be the integral of For those of you who know calc, if you don't know calc, don't worry about it. It's going to be the integral of e dx. And there's like a dot product mixed in there too, but oh, it's a negative sign. I dropped the negative sign because I'm bad. And another note, just for the record, for a positive charge, the higher the potential difference, the higher the potential energy. But a negative charge, the higher the potential difference, the more negative the potential energy, which is kind of weird. But once again, this goes back to everything's backwards. All right, let's do an example problem before I get too crazy into this. So let's say we got a point charge of -2 coulombs. And it has a potential energy of 2 joules at point A and 5 joules at point B, and are 1 meter apart. What's the potential difference? And I did A minus B here instead of B minus A. All right. What's the potential difference? And which plate has positive charges? Well, if I want to find what's the potential difference and which one's the positive charge, I can say the potential energy is greater next to the rightmost plate. Since Q is negative, and if it has more potential energy here, it has to be like this. Because it's going to be, normally the potential energy is close to the positive plate, but we're negative, so it's the opposite. Then it says, what's VA minus VB? Well, VA minus VB is just delta V, delta PE over Q. And so the potential difference will be the change in potential energy over the charge. 2 joules minus 5 joules over -2, or 1.5 volts. So I can say the potential difference between these spots, or the voltage between these spots, is 1.5 volts. Any questions? Okay. It also asks how much energy does it take to move the 5C charge from B to A? Well, the energy to move it is just going to the change energy to Q delta V. Why did I? Oh, to move a 5C charge. So if I have a 5C charge instead, I would just do 5C instead of my -2. It would take 7.5 joules. And lastly, what's the electric field between the plates? Electric field, I can use this equation. And rearranging, I can get my electric field. Okay. Now, I admittedly haven't gotten to a useful place with any of this yet. It's empty because I'm not doing anything with this voltage yet. But there's the general idea. One of the things that makes this useful, though, is that energy is energy. It doesn't matter what type of energy you have, it's still energy. And we have conservation of energy. Your initial kinetic plus potential energy must equal your final kinetic plus potential energy. Now, if I rearrange this, if I subtract kinetic energy A from both sides, then subtract kinetic energy, potential energy, sorry. No, I subtracted kinetic energy A from both sides and subtracted potential energy B from both sides. I could say that the change in kinetic energy must be the negative the change in potential energy. Remembering that kinetic energy is 1/2 mv squared. And what this does is we can figure out how fast an electron or proton would move if it's put in an electric field. Because if it's put in an electric field, you can find out what the potential difference is. And if you know the potential difference, you know the change in potential energy. If you know the change in potential energy, you know the change in kinetic energy. Because putting together this line here and this line here, I can say that QV is delta PE or delta -KE. And this is how we accelerate charges. If you want to make a charged particle move, we normally don't talk about putting in an electric field. It's what you're doing. An electric field is what causes a potential difference. But anytime you want to give a charged particle some velocity, we talk about applying a voltage, putting it in an electrical potential difference. By applying a voltage, we can give it an equivalent change in kinetic energy. Now, here's the other crazy thing we do. When accelerating, we're going to do the positive charges for now. I'll come back to negative charges in a second. But if it was a positive charge, we normally talk about accelerating from a region with some voltage V into a region of no voltage. We talk about, if we're going to have a, if we keep having delta V, right? If delta V is going to be V final minus V initial, let's just define one region as 0. If we define one region of 0, then it's just going to be, delta V is just going to become V. And what we say is we normally put something in a region of voltage and let go, and it gets shot out till it goes in a region of none. That V final is usually goes to 0. Which means, plugging that into my equation above, that QV is delta KE, where V is the initial potential difference. And this will give us this idea that if you put a particle in a region with a voltage of V, it'll accelerate to that speed. Now, this is really weird because V, once again, should be potential difference. So having V and not delta V doesn't fully make sense. But this is just how we recode it. Really, it should be a potential difference. It should be measured between two spots. But we just always say, okay, it's going from this region with some voltage to this region with none. Let's just only refer to it by the initial voltage. And I dropped my sub I because it's so common to do it this way, no one ever puts it there. They just say V. Now, I could rearrange that equation further and solve for velocity. And yeah, that's the value. Now, this is something kind of weird because this was all done assuming a positive charge. But let's say it's a negative charge. If your charge was negative, you'd be plugging in a negative value for Q. And if your charge was negative, that means you'd be taking the square root of a negative number. It's not possible. This goes back to Benjamin Franklin had it backwards. But here's the thing. If Q was negative, let me go back a slide. If Q was negative, it would accelerate the other way. And if Q is negative, that means this one would be 0. And this one would be just regular V. And so if Q is negative, it would be delta V is just V instead of negative V. And so what happens is when Q is negative, suddenly a negative sign shows up inside this equation. Oh, I do have it on the next slide. Sorry, I didn't think I actually had it though. Here we go. And since that's going in the opposite direction, these equations come out as so. That if you have a positive charge, it's the square root of 2qv over m. If it's a negative charge, it's the square root of negative 2qv over m. And so it's easier just to say it's the square root of 2qv over m absolute value, because it will work out the same either way. Okay? Now, this is used a lot. When you want to put energy, when you want to put a current, we haven't gotten current yet. When you want to power something, you plug something into a wall. This is what's happening. There is a electric potential difference where we define one of the two sides as 0, and we cause that to move electrons. The moving electrons creates a current. One of the most obvious ways to see this is an old school television set. Old school, like the wide CRT televisions, literally how they work is they apply a voltage at the back and they accelerate electrons that go flying forward and hit the screen. A good TV would have about a 25 kilovolt voltage to accelerate electrons. Let's say they do that. There's the mass of an electron and the charge of an electron. If I put an electron in a 25 kilovolt potential or voltage, potential or voltage, same thing. We can say, what's the speed when they hit the screen? Because the velocity would just go by this. So I can plug in values. I can take my absolute value and get a speed. And the answer is you get like relativistically high, like close enough to the speed of light that you probably should be dealing with the speed of light and what that means, which is something we'll cover at the very end of this semester. But you can really get something going quickly. Now it seems weird I didn't give the distance, but that's because once again, we're assuming that we're starting in this potential of voltage of 25 kilovolt and going into one with none. Questions?
Nope, I got it.
All right. So here's another thing. This all started with potential energy. So let's go back though. We know that between 2 point charges, we can have a force. And from 1 point charge, we can have a electric field. But the thing is, if you create an electric field with 1 point charge and you bring another point charge button towards it, you're moving that point charge in an electric field. It won't be a uniform electric field since the electric field depends on difference, but you are still moving that point charge in an electric field. If you do a bit of math with those calculus I talked about before, you can actually find that anytime you have 2 point charges, there will be a potential energy due to the location between them as KEQ1, Q2 overall. Now this does admittedly look a lot like the force between two charged particles, right? Because the force between two charged particles is KEQ1, Q2 over R squared. But there's two major differences here. The big one, is that we don't square the distance. But the more important one is that force is a vector. The potential energy is not. And so anytime you have 2 point charges, you can say that there is a potential energy. They each feel a potential energy. If you have 2 point charges, 1 and 2, number 1 will feel a potential energy equal to this equation, and number 2 will also feel a potential energy equal to the same equation. If both charges have the same sign, potential energy is positive, which makes sense. Energy is normally positive. What that means is positive work must be done to force the two charges near each other. It makes sense. You got a proton and a proton. They don't want to get closer. So if you take a proton and proton and shove them up, you're increasing their potential energy. Because by pushing them together, you're just preparing them to go shooting out. Think of it a lot like springs, like we had done in Physics 1. That if I take a spring and compress it, I'm just getting it ready to shoot open again. Same if you take a positive and positive or a negative and negative and compress them, you're giving them potential energy ready to shoot out. But of note, if you have a positive and negative, your potential energy is negative. And I know I've said before that scalars shouldn't be negative, but that's not true. Some scalars can be. And this is one of them. If you take a positive and negative thing and try to move them together, they want to go flying into each other. So if you put them here and let go, they just go phew, together. So if you go and try to move them forward, you're decreasing their potential energy because you're bringing them where they want to go. And so a positive and negative will have a negative potential energy. Now note, for the first time, I am not putting absolute symbols around my equations. That is important. It's a scalar, the direction doesn't matter. But it does matter what the sign is, whether it's positive or negative. Okay? Okay, let's do an example problem. Let's say I want to make this setup in the bottom right. I want to take a 1 microcoulomb, a 2 microcoulomb, and a negative 3 microcoulomb charge. And I want to set them up as displayed. How much work would it take to create this? That's my question. If I want to find out how much work it would take to acquire this, I would just have to figure out how much energy it would have to make it. And what I can say is, okay, I got 3 charges. I need to put all 3 in. Let's start with the first one. I'm going to take my first charge and put it on my sheet. When I bring my first charge in, it's the only thing there. I can just place it, no issue. Just whoop, it's good. But let's say I then go to add my second charge in. When I go to add my second charge, that's going to take some energy because now there's another charge. And the amount of energy it's going to take is going to be the final minus the initial potential energy. But keep in mind, I took it away from infinity. My initial is going to be 0. So the amount of energy it's going to take is just however much potential energy it ends up with, which goes by KEQ1Q2 over all. And so to add that second charge, we'll take 0.0036 joules. It'll take 0.0036 joules because that's the amount of energy it takes to put Q2 near Q1. So, okay, we got that guy though. But that only makes half the thing. Or 2/3 of the thing, I should say. Let's move in the third charge. When I move in the third charge, I'm still taking it away from infinity, so I still have no initial. And I can say when I bring in this third charge, it's going to have potential energy from Q1, but it's also going to have potential energy from Q2. And so its total potential energy will be the potential energy from 1 plus the potential energy from 2. Which I kind of factored this out a little bit to make my math easier. Right? Because it was KEQ3 over all is the same for both. And so the potential energy to bring in the third one is going to be KEQ3 over all times Q1 plus Q2. And it will take it this many joules to be put in. And therefore, the total energy it takes to create this will be the energy to add the first one, which was 0, plus the energy to add the second, which is 0.0036 joules, plus the energy to add the third, negative 0.0161 joules. And so it actually would take negative energy to do it. It'll just suck itself right in once you start bringing the third guy, because it's a negative value. Okay? Not getting as far as I expected. Now let's go back to the idea of potential difference with this. See, this was dealing with the potential energy from a point charge, where the potential energy was KEQ1, Q2 over all. But this was just, let's just say that, okay, same way that electric field was a force taking away a charge, we're going to say that we said the change in potential energy divided by charge was the change in voltage. And if the potential energy on a point charge Q naught from another point charge is given as this equation, if we want to move from point A to point B, we could go like follow through this, right? Same idea we've been doing. But we already said delta PE equals Q delta V. And if I just plug in those for my PEs, that means Q delta V equals QVB minus QVA equals the same thing I had. So I'll just divide out a Q naught. And what that means is the potential difference between two charges for a point charge will be KEQ over all. Once again, this involves moving it from one spot to another, though. However, if you do not move, if you make one of those two spots infinitely far away, if we say that we take this charge from infinitely far away and bring it in, from off the screen way over here that you can't see to where we're going, we can say that RA came from infinity. And if RA is infinite, something divided by infinity limit goes to 0. And then we can say, okay, instead of delta V, we can just say V at a set spot, the voltage at a set spot. And we can define the voltage as Coulomb's constant, the point charge over all. And this is what we're going to say, that for any point charge, it has an electric potential of KEQ over all. because we're saying the electric potential difference is between that number and 0. But that would be the electric potential of a point charge. Now, this does assume that we take infinity to be 0 volts. And we're always going to make that assumption. We're going to make 0 infinity. It makes life easy. But this is just the potential, this is just the voltage or electrical potential. And note, I'm no longer saying electrical potential difference. Electrical potential difference is delta V. Just V is potential difference. But this is just for one point charge. If you have multiple point charges, the total voltage is just the sum. You just add them up. And from this, we can find the potential, the electric potential of complicated setups. Now, I'm going to throw something out here. The last chapter, the homework and everything, had a lot of dealing with find the electric field at this point, find the forces on these charges, and it had a whole bunch of shit with vectors. That was a real pain in the ass. We're doing basically the same thing here, but it's all scalars, which makes it so much easier. You don't have to deal with any vectors in this. You just do the math and add it, and ignore all vectors. If you want to solve one of these problems, you normally got a diagram of the charges, draw it, calculate the distance to each point, and just use this equation. You can ignore what direction they're in. It's not a vector. It doesn't matter. It's just going to be KEQ over R. It's the distance that matters and nothing about from where, making this so much simpler than what we did last chapter. That's right, this is empty. Okay? Let's do a problem then. Same setup. What is the electrical potential halfway between Q1 and Q2? So what's my electric potential right there? If I want to find my electric potential right there, I just find what it is from each one. Now I do need to know the distances. The distance from Q1 to that point is 2.5. Distance from Q2 to that point is 2.5. For the distance from 3 to that point, I need to use Pythagorean theorem. Well, R1 squared plus R3 squared is 5 squared, which I can rearrange, do some math, and solve for. And so I can say, okay, R1 is 2.5, R2 is 2.5, and R3 is 2.5 squared of 3 over 2, or 4.33 meters. But from that, I can find each voltage. The voltage is KEQ over R. I dropped my E there, just KEQ over R. I don't know why there's no E. And so V1 is KEQ1 over R1, and I can plug in. V2 is KEQ2 over R2, and I can plug in. V3 is KEQ3 over R3, and I can plug in. But the total potential, total electric potential is just the sum. And I just add them up and get the answer, ignoring all vectors. Nice and simple. These are so much easier to deal with than forces in an electric field. Any questions? Okay. So what that means so far this class is we have Coulomb force, electric fields, electric potential energy, and voltage. And all of them have very similar looking equations. For one charge, the electric field is KEQ over R squared, while the voltage is KEQ over R. That's what you can describe what surrounds one charge. Where electric field must be a vector, voltage is not. For any pair of vectors, or pair of charges, I misspoke, we can talk about the force between two and the potential energy between two, which also have very similar equations. But force is a vector, potential energy is not. Keep in mind that you must pay attention to the direction and magnitude for the vectors, but the signs for scalars. You don't, if you remember, I kept putting in absolute value signs when solving for electric field and force, and just use the direction by looking at the picture. That's fine. But when solving for voltage and potential energy, you need to worry about the value for Q. Is it positive? Is it negative? All right, let's go back to something we had talked about last class then. Last class, we had said that all points on a conductor, that on a conductor that there's no electric field inside of them. Is one of the things I said. The reason that there's no electric field inside a conductor is all points on a conductor will always have the same potential or electric potential. The reason for that is the charges moving up there out. If you move from point A to B on the surface of a conductor, it will always take zero work, since your delta V is 0. Now, last time we said how all the charge was on the outside, and this is part of the reason why. Is because inside they have the same potential. Inside a conductor, the potential is the same at all points. And since there's no work to move the charge, it's going to move it the furthest out as it can to be as far as possible. This also ties into the idea of equal potentials, which was something in the lab that I released Thursday that I don't know how many of you looked at yet, but you're talking about equal potentials even though I haven't taught it yet. An equal potential is an area where the potential is the same. That each of these blue rings on these charts are areas of equal potential. They're just, on each line, the potential is the same at all spots. Now, for a point charge, it makes sense it's rings, since potential is given, don't have it though, potential is given as KEQ over O. So it's just concentric rings. And in fact, around any combination of charges, you can draw equal potential lines. And it's a kind of a neat thing. Equal potential lines are always perpendicular to an electric field. At all points, the electric field will hit the equal potential line perpendicularly, always. And so actually, if you map equal potential lines, you can map electric fields, which is your first lab. Okay?
Why is it for B there? It doesn't show. There's no like arrows that are coming from the from that positive or the positive charge to the negative side. It's only going from the negative to the positive.
It's
Shouldn't there
going from
be
the,
a
what
click
do you mean?
there?
These are going from positive to negative.
Shouldn't there be arrows on from both sides or no?
No, because it goes from positive to negative. So the electric fields always go into the negative charge and out of the positive. So the arrows always point the same way.
Oh yeah, okay.
I don't
Yep.
know why this hand is here. All right, does that answer?
Yep.
Okay. So with my last 5 minutes, I want to start the next big hunk from this chapter, a little behind where I want to be. And that is, people have learned how to make devices to store charge in such a way to create potential differences and to create a potential devices to hold electric fields and to hold the electric fields to create potential differences to cause the movement of electrons. And the most simple one is this guy right here. This is what's called a capacitor. And a capacitor is something that can be used in electric circuits to add in a potential difference. What a capacitor is two metal plates separated by some distance. Most capacitors are referred to as parallel plate capacitors. They consist of two metal plates that are just parallel next to each other, parallel plates. A cylindrical one like this, which is what you normally find if you buy like a capacitor in the store, consists of two ringed plates. One like this and another one outside, just forming a cylinder going down. But if you look at dead on, it's kind of just two rings. What happens is if you do something to create these plates, what you can do is if you apply a potential difference across the plates will become charged. Where one plate will have a charge Q and the other plate will have a charge negative Q. And once they have this difference in charge between the two plates, once one is positive Q, one is negative Q, well, if I do that, that's going back to this stuff from way back at the beginning of the day, right? If I give one a positive charge and one a negative charge, that's causing an electric field. And if I'm causing an electric field, I can cause a potential difference. And so if you apply a potential difference, you can force the charges to be different, and then you can take away the potential difference, and it will stay there. We can then define the capacitance of each one of these, where the capacitance is the amount of charge you got on the plates versus divided by the potential difference between the plates. Really, I put a V here. I didn't put delta V. It should be a delta V. But the thing is, people just arbitrarily mix up V and delta V. Delta V is potential difference. Well, delta V is electric potential difference. V is electric potential. But because we just always say zeros at infinity, we just use V instead. And even though when it shouldn't be zero, it's the difference between this plate and that plate. Oh, this plate and this plate. So really nothing should be zero, but we just still say the change between the two, we put a V. We don't put the delta. That's just standard. Mathematically and physics-wise, it's kind of wrong, but it's the standard. And we define the capacitance, which uses the symbol C, once again, is the charge over the potential difference between the plates. Of note, capacitance has its own unit of farads. Farad uses the symbol capital F, where 1 farad is a coulomb per volt. Now, if you have a parallel plate capacitor, like the type I talked about, it'll just be two plates, one with a positive charge, one with a negative charge, separated by a distance d. If there is nothing in between the plates, if it is vacuum or air is close enough for vacuum. If there is nothing between the two plates, the capacitance can actually be given by the shape of the capacitor. That if you have two parallel plates, I'll keep using this dice case. If I have two parallel plates, I can say the capacitance, aka how much voltage per charge they can hold, or how much charge per voltage they can hold, I said that backwards, can be given as so. C equals epsilon naught A over D. Epsilon sub naught is the permittivity of free space. I mentioned last class, or last chapter, that Coulomb's constant was actually based off a more important constant. And I said that Coulomb's constant is actually 1 over 4 pi epsilon sub naught. I kind of mentioned in passing, but that's it. That epsilon sub naught is the same one here. That's the permittivity of free space. It's a much more important constant, but most people with Coulomb's law just keep it as Coulomb's constant. But this will actually give the capacitance for each thing, assuming there's nothing in the middle. If there's something in the middle, you include something called a dielectric constant that basically puts something in the middle. Instead of epsilon sub naught, you put epsilon. And you change the constant epsilon sub naught by a certain amount. But if we can say for any capacitor, what this does is if you know the area of each plate, because that's what A is, the area, and D, the distance between the plates, you can figure out exactly how much charge is needed to apply to hold how much potential difference, or vice versa, depending on what your goals are. Also, if we're just looking at two parallel plates, we know that between two parallel plates that the change in voltage is E delta X. So that means in any parallel plate capacitor, it'll have an electric field of the voltage over the distance between the plates. And so if we add a charge, it can create this potential difference. Okay? Now, I actually am a minute over, although I started a minute late because I started recording without my mic on. That's going to be cut out of the video. So, actually, it's a separate video, I guess. So I am going to end there. Well, next class we're going to really get into what to do with capacitors. Sorry, no real demos today. This stuff is a little confusing, I admit it. If you have any questions, let me know. But otherwise, there you go.
Homework's due on Wednesday, right?
Say it again?
Homework's due Wednesday.
Yep, homework is due Wednesday.
Okay.
Otherwise,